If we are interested to determine the energy in two-dimensional system, then we can take example of energy of simple pendulum, potential energy of simple pendulum. So let us consider a simple pendulum having three length L and bob having mass m, on which we are applying a horizontal force F, due to which it is displaced from its equilibrium position, that is simply as origin O, y position A, and got that angular displacement, that is theta naught. In this position, the vertical displacement got by the particle is simply h. In that position, the burden by the force F, which is simply horizontal force, can be written as simply that is W equals limit from O to A Fx dx plus Fy dy. Okay, but as I said that this is the horizontal force, so in that position we have the value of Fy, which is simply the force exerting on the y-axis, vertical axis, which is simply equals to 0, and let Fx equals to F. By put this value in our equation, we get limit from 0 to A and F dx. Let this equation is 1. Now from the diagram we can resolve the two components of the tensor in the string. These are simply F equals T sin theta and mg equals T cos theta. So let me write down here. This is F equals T sin theta and mg equals T cos theta. Okay, by dividing these two equations we get F over mg, that T is cancelled by T, and sin theta over cos theta gives tan theta, or F equals mg tan theta. Okay. Also from the diagram we can determine the value of tan theta from this minor triangle, which gives dy upon dx. Here simply dy is the perpendicular and dx is the base. So dy upon dx simply gives the tan theta perpendicular upon base. So I can write also mg into dy upon dx. By putting this value in equation number 1, we get w equals integration mg dy over dx into dx. Dx is simply cancelled by dx. Now let us point out the limit of the bob, which is displaced from equilibrium position from O to A. In that position the maximum height got by the particle is h. So let me write down the limit for this integration, which is simply equals 0 to h. 0 to h. By integrating this, first of all, these are m to g are both a constant, so I can take as out from the operator of integration, that is mg integration 0 to h into dy, which gives me mg into h. Okay, so this is the work done by the horizontal force which is applied on the bob to displace it from its equilibrium position to A. Now simply this energy will be consumed as the potential energy of the simple pendulum. So I can write this work done will be equal to the stored potential energy in the simple pendulum. So here this work done is equal to the potential energy of simple pendulum. Okay, and the potential energy of simple pendulum can also be written as u x comma y. Here y is simply h. So I can also write this x into x comma h, which have determined as mgh. Okay, let this equation is 2. In that position, you can see that here A is the maximum position got by the particle. So in that position, the velocity of the particle, velocity of the bob will be 0. So that in this position, the kinetic energy will also be 0, because kinetic energy depends on the velocity and the mass. So velocity is here simply 0, so kinetic energy will be 0. But in that position, only and only potential energy will assumed by the particle. So I can also say that this is the maximum position got by the bob. In that position, the particle, the bob will also will possess only and only potential energy. Now let us consider an intermediate position between O and A in any position. So I have drawn this position as the theta is the angular displacement in the intermediate position from O to A of the bob. So in that position, the particle will consume the both type of energy, which are simply kinetic energy and potential energy. And why it is so? Because in that position particle is moving from O to A or O to A to O. So in that position the particle is moving between the O to A. So simply the kinetic energy will consumed by the bulb. So in that position let the V be the velocity of the bulb with which it is moving. So in that position the kinetic energy of the bulb will be kinetic energy equals half mv square, and simply the potential energy in that position will be mgy. Here y with the displacement got by the bulb in vertical direction. So in that position the total energy consumed by the bulb will be, I am writing is that E is the kinetic energy plus potential energy, which is simply known as the mechanical energy. So here K is half mv square and plus that is mgy. And in earlier case we have determined the maximum energy got by the bulb, which simply was mgh. So I can also write here E equals mgh. So mgh equals half mv square plus mgy. Here m is common in both terms, so I can cancel by taking common s and get this is simply gh, and this term will be taken as if negative. Gh minus gy equals that is v square upon 2. Also here v square equals that is 2 multiply g is common, g and h minus y, and v equals square root of 2g into h minus y. So this expression shows the velocity with which the bulb is moving. Now let's know how to prove a given force as a conservative force or non-conservative force. So if you want to prove a given force as conservative or not, then you will have to find the curl of the given force. If the curl of the given force equals to 0, then you will able to say that the given force is conservative. And if the curl of the given force is not 0, then the force will be called as non-conservative. So here the question says if a force vector F equals 2xy plus z square I cap plus x square j cap plus 2xz k cap, this so that it is a conservative force and also determines potential energy function. So let me prove here this force is conservative or not. So first of all I will find the curl of the given force, and before I begin to prove this let me compare this equation as a general vector form of the force, which is simply given as vector F equals fxi cap plus fy j cap plus fz k cap. So by comparing the given force with this, I get fx equal, which simply equals 2xy plus z square, and fy equals vector y equals x square and vector fz equals 2xz. Okay, now the curl of the given force is written as curl of force, which simply can be determined del x, del y and del over del z. And let me write down the coefficient of fx, fy and fz, which are simply 2xy plus z square. This is the coefficient of fx, and x square. This is the coefficient of y, and the coefficient of fz is 2xz. Now let me solve this. I, and here this portion multiply by this and minus this portion multiply by this. So I have given this multiply by this, that is 2xz over del y and minus del x square over del z and minus j cap. Also this portion multiply by this and minus this portion multiply by this, and I get del 2xz over del x and minus del 2xy plus z square over del z. Okay, and plus k cap, which simply gives us this multiply by this and minus this portion multiply by this. So del x square over del x minus del 2xy plus z square over del y. Okay, now we can differentiate this portion. Here the differentiation of this portion with respect to y is simply 0 because y is not appearing here. So I can write is at 0 and minus. here also this portion will be 0 because there here z is not appearing, and minus j cap. Here the differentiation of this portion with respect to x is simply 2z because x becomes 1, and minus here differentiation of this portion with respect to z is simply 2z because this portion will be 0. So 2z and plus k cap, and here the differentiation of x square gives 2x and minus differentiation of this with respect to y, which gives us 2 into y, 2 into x, because z square is 0. Now you can see on the board here all terms become 0. So we can write as the curl of given force equals to 0, and this was to be proved. As here the curl of the given force is equals to 0, so we can say that the given force is conservative force. So F is conservative force. And now remaining to determine the potential energy function of the given force. So simply the potential energy function of the given force is given by U equals minus integration F dot dr. So the given force here is minus Fx dx plus Fy dy plus Fz dh. Let me write down the value of Fx, Fy, Fz here, which are Fx equals 2xy plus z square into dx plus Fy, which is simply equals x square into dy and plus Fz. This is 2xz into dz. Okay, so we can integrate this equation, and before it, let me rearrange these terms. I can arrange these terms as 2xy into dx and also x square into dy and also z square dx and plus 2xz dz. And you can see on the board that these two terms are the derivative of simply x square into y, and this is the derivative of z square and x. So I can write here as simply x square y, or plus this is the derivative of x square y, and this is the derivative of z square x. So here the derivative will cancel by the sign of integration, and which gives us to simply x square y plus z square x. So this is the potential energy function of the given force. This numerical problem says that the electric potential in a system is given by Vx by z equals 20 plus 6x square minus 5xy plus 4y square plus 3z square joule per coulomb, where x, y and z are meter. Reduced in IJK notation, the force on a 2 into 10 raised to power minus 15 coulomb charged placed at position 2, 0, minus 3 meter. So let me write down the given potential function, which equals Vx y z 20 plus 6x square minus 5xy plus 4y square plus 3z square joule per coulomb. And also we know that the negative derivative of electric potential gives us the electric field. So I can write as E equals del V upon del X plus del V upon del Y plus del V upon del Z, which shows the negative derivative of electric potential gives us the electric field. And also the position which is given to us of the charge is 2, 0, minus 3. So we can differentiate the given equation partially with respect to x, with respect to y and with respect to z separately, and then put down the value of del v upon del x, del v upon del y, del upon del z from this equation as here. So when we differentiate the given potential function with respect to x partially, I get this is 12x minus 5 by I and plus minus 5x plus 8y j plus 6z. Okay, so this is the differentiation of this equation as accordance this equation. So when we put the value of position of the charge, which is given to us 2, 0, minus 3 in this equation, we get E equals minus 12 into 2 minus 5 into 0 I plus minus 5 into 2 plus 8 into 0 j plus 6 into minus 3, which simply leads to 24I minus 10j minus 18k. Okay, so this is the electric field under which the charge is placed. Now we have to find the force on a 2 into 10 to the power minus 15 coulomb charge, which is given by F equals QE, where F is the exerting force or the charge placed in electric field E. So let me write down the value of electric field as here. F equals Q into minus 24I minus 10J minus 18K. And the value of charge is given to us, that's it, 2 into 10 to the power minus 50. So the value of charge is 2 into 10 to the power minus 50. And let me introduce this negative sign in the bracket that leads to this equation minus 24I plus 10J and plus 18K. And also we can rearrange, we can solve this equation by multiplying by 2 in the bracket, which gives us 48I and plus 20j and plus 36k into 10 to the power minus 15, and the unit of force simply is Newton. So this is the required expression which